You've probably used an AI that can find one specific image among billions. Or maybe you've wondered how a chatbot can instantly pull a single fact from like a whole library's worth of books. Well, what you're really asking about is something called vector search. And today, we're going to pull back the curtain on Faiss, that's Faiss, the open source library for Meta that's become the quiet, unbelievably powerful engine that makes all of that searching possible.
You see, the thing about modern AI is that it's not just processing the data we give it anymore. Nope, it's creating a whole new universe of its own data. Every single image, every sentence, every little piece of audio, it can all be translated by an AI into a really special kind of data point. And this new kind of data? Well, it needs a whole new kind of map. And that map is built with a concept called embeddings. Now, the easiest way to think about an embedding is like a GPS coordinate for meaning. An AI takes a piece of content, let's say a picture of a golden retriever, and it gives it a coordinate. And here's the magic. It'll place that coordinate right next to pictures of other golden retrievers and, not too far from pictures of other dogs. It's a map where the location literally equals similarity. But this, of course, raises a huge, huge question. What happens when your map doesn't just have thousands or even millions of coordinates, but trillions of them? How on earth do you find anything fast enough for it to actually be useful? This right here is what the industry calls the billion vector search problem. And it's a challenge of almost unimaginable scale, where frankly, all the old ways of searching just completely and totally fall apart. Just to give you an idea of what we're talking about, a single real-world content moderation system might need to search and index with 1.5 trillion vectors. I mean, look at that number. That's a 15 with 11 zeros after it. The scale is it's staggering. Okay, so the simplest way to search, right? You just check every single point. You take what you're looking for, compare it to all 1.5 trillion other points on the map, and find the one that's closest. This is called a brute force search. And yeah, it's perfectly accurate, but at this scale, it's also impossibly painfully slow. And this creates a fundamental dilemma. Do you want perfect accuracy, which is so slow it's basically useless, or do you want something that's actually fast? Now, in these massive data maps, there's this weird quirk where everything is strangely far apart from everything else, which makes brute force even less practical. So, modern AI has made its choice. It relies on what's called approximate search. The idea is to trade a tiny, tiny bit of perfect accuracy for a massive gain in speed. And that's what makes the impossible, well, possible. And this is exactly where Faiss comes into the picture. Faiss is the master of this trade-off. It's not just one single algorithm. Think of it as a whole toolkit, designed to solve this completely impractical problem in a really, really practical way. So what is it? Well, it was developed at Meta AI. And it's a library for exactly this, Approximate Nearest Neighbor Search, or ANNS for short. Its entire reason for being is to find the good enough neighbors, the most similar items, in a gigantic dataset at lightning speed. This quote from the original FAST paper, it just perfectly captures the whole philosophy here. The creators point out that for most real-world tasks, finding the absolute, mathematically perfect closest match, it just isn't necessary, right? If you're searching for pictures of golden retrievers, the second or third closest image is probably just as good as the absolute number one. Which makes you think, why would you waste all those precious milliseconds, all that computing power, striving for a level of perfection that doesn't actually make the result any better? The key insight here is that being good enough is often the truly perfect solution. Faiss lives right at the center of these three competing goals. You want your search to be fast, you want it to be accurate, and you want it to use as little memory as possible. Here's the catch. You can't maximize all three at once. It's a classic trade-off. Faiss is what gives developers the knobs to turn, letting them fine-tune that balance for whatever their specific need is. So how does it do it? How does Faiss actually achieve this incredible speed? Well, it really boils down to two big, really clever ideas for searching smarter, not harder. The first big idea is vector compression. It's a simple concept. If your data points, those GPS coordinates we talked about, are really long and detailed, they take up a ton of memory and they're slow to compare. So Faiss uses these smart techniques to shrink them, making them smaller and way faster to work with. It's basically like shrinking the map before you even try to read it.
And this is a perfect example of that toolkit idea I mentioned. It's not just one compression method. It's a whole suite of different options. You've got things like scalar quantization, product quantization. You don't need to know the details, just that each one is like a different tool for a different job, giving developers the exact right one they need. Now, the second big idea is maybe even more important. It's called non-exhaustive search. And the thinking here is simple. Instead of looking at every single point on that massive map, Faiss intelligently divides it up and only searches the neighborhoods that are most likely to have your answer. One of its most popular methods for this is called inverted file search, or IVF. The logic is just beautiful. So first, before any searching even starts, Faiss pre-organizes the entire map. It groups billions of vectors into thousands of logical clusters, these neighborhoods. Then when a new search comes in, it doesn't have to check every single point. It just quickly figures out, say, the 5 or 10 most promising neighborhoods, and only then does it do a detailed brute force search, but just inside those few small areas. This pre-sorting is what cuts down the search space so dramatically. Okay, so let's bring this all together. Let's see how this stuff actually builds into real-world applications. Because these ideas, they're not just academic. They are the absolute foundation for some of the biggest AI systems on the planet. I mean, Faiss is used for content moderation at a trillion vector scale. It's the engine that lets large language models retrieve the right documents to answer your questions. It's used to find duplicate images across datasets with over 1 billion photos. It's so fundamental that it's actually the core engine inside many of the major commercial vector databases that big companies rely on every single day. So when you put it all together, you realize Faiss isn't just another library. It's a critical piece of the unseen infrastructure for the entire AI ecosystem. It's that foundational layer that just works, humming away quietly in the background, turning a computationally impossible search problem into a solved one. It's the thing that allows so many AI applications to feel instant and, honestly, kind of magical. And its importance is no secret in the tech world. With over 37,000 stars on GitHub, it's one of the most popular and trusted tools for developers working on the cutting edge of AI. That number, it represents a massive community of builders who depend on Faiss every single day. And that really leaves us with a final thought. Faiss solved the billion vector problem, and then it helped solve the trillion vector problem. But AI is not slowing down. If anything, it's speeding up, generating vaster, more complex universes of data every single day. So the real question is, what tools and what new big ideas are we going to need to map the next frontier?